Hi, well, I'm Stephen Neshima, and I'm here to help you out with some calculations regarding calculating the enthalpy of formation and the enthalpy of reaction. The reference on all this is table A4.3, where all these numbers are tabulated. So the first idea here is that we have substances in their standard states. Oxygen, for example, is a gas at room temperature. That's its standard state. Hydrogen's a gas. Carbon, pure carbon, is graphite. It's a solid at room temperature and pressure. So that's the idea of a standard state. Now, what I've written up here are actually pure elements in their standard state, because that's pure oxygen, pure hydrogen, and pure carbon. And now, the reason that that's important is something like this. When we're talking about what's called the enthalpy of formation, that's given by a delta H naught subscript F, that's for formation, we're thinking about a chemical equation in which on the left-hand side of the area of the arrow, I have pure elements in their standard states, like these guys here. And on the right, I have one compound or one substance. The point is it's got a stoichiometric coefficient of 1. So let's go through some examples, and we'll just sort out whether this really qualifies as a delta H naught of formation type of reaction. How about this first one here? Well, let's see, I've got hydrogen, pure H2 in its standard state. That on the left, that's good. And on the right, I have just a single substance, H, with a stoichiometric coefficient of 1. That's just implied if you don't write it. So, okay, that does qualify. And if you look up in table 4.3, you will get the number 218 kilojoules per mole, okay? That is the enthalpy of formation of 1 mole of atomic gaseous hydrogen. Okay? How about this one? Does this one look like it qualifies as being a standard enthalpy of formation reaction? Well, I've got one compound on the right, stoichiometric coefficient of 1. On the left, pure elements in their standard states. So you bet that qualifies. And as it turns out, the delta H naught of formation is minus 394 kilojoules per mole. Okay, how about that third one? You might want to just give this think about this for a moment. Okay, well, I'm hoping what you decided was that it's not an enthalpy of formation reaction. There are actually two problems with it. One of them, I have two stoichiometric equivalents here on the right, a stoichiometric coefficient of 2. That disqualifies it. Here's the other problem, is on the left, I've got CO2. That's not a pure element. It's a compound. So there are two reasons why this is not an enthalpy of formation reaction. Now, we can still analyze this kind of reaction. We can analyze any reaction just by considering a different type of value, which is called the enthalpy of reaction, and that's given by the simple delta H naught sub reaction. Okay, what this number tries to do is it tries to calculate the change in enthalpy when those reactions happen. And the way we do that in general is we say, okay, I'm going to add up all the enthalpies of formation of the products, everything on the right-hand side of the arrow, and then subtract away all the enthalpies of formation of the reactants. So I have a separate example here for you. This is the combustion of methane. So methane combines with molecular oxygen to make CO2 and water in its liquid state. So what I'm going to do first is I'm going to write down the delta H naught of formation of each one of these. So let's see, we've already got CO2. We already looked that one up. That's minus 394. Minus 394 kilojoules per mole. And now for water, you'd have to look that up, and you'll find a different value if it's gas or liquid. But since I've got liquid here, I'm going to write down minus 286 kilojoules per mole. So now that's this part. Now we'll have to take into account before we're done the fact that there are two of those in this equation. But I'm going to finish this table here. If you look up the enthalpy of formation of oxygen gas, well, oxygen is actually already a pure element in its standard state, and that's 0, and you'll find that if you look up oxygen, molecular oxygen in table A4.3. And then the last bit is methane. That turns out to have a delta H not a formation of minus 75. So how are we going to use this equation? Well, I'm going to add up all the enthalpies of formation of the products, and that's this. So I'm going to say I have a minus 394, okay, minus 394, and now I'm going to add on to that twice minus 286, so I'll say minus twice 286. Okay, that takes into account that stoichiometric coefficient, and there was a minus sign there. So that's this whole term here, and now I subtract away all the enthalpy of formations of the reactants. I've got methane, that's minus 75. Okay, and I have oxygen, but that's 0. It would have been twice 0, but that's still 0. So I'm all done with that, and if you add up all these numbers, you get the number minus 891. That's kilojoules per mole, the enthalpy of reaction for combusting methane. Okay, that's it.